Section 2.3, the limit laws. In the previous section, we looked at graphs and tables to approximate the value of a limit. In this section, we're going to look at algebraic and analytic approaches to find the exact value of the limits without relying on the graph or tables. We'll start off with two basic limit results that will tell us the exact value of a limit. For any real number a and a constant number c, the limit as x approaches a of c will equal c, while the limit as x approaches a of x will equal a. The reason why the first property holds true is that the constant function f of x equals c is a horizontal line. So no matter what our x value is approaching, as we trace from either side of x equals a, we are staying on the horizontal line. So f of x equals c will be approaching c because at every point the y component is c. The reason why the second property is true is because the question answers itself. If x is approaching a, then what is x approaching? Since it was told to us that x was approaching a to start, x would be approaching a. Now, using these properties to evaluate, we do want to be careful and pay attention to variables to distinguish what is considered constant and what is our actual independent variable. So for our first example, we have the limit as x approaches 2 of 5 pi. X is approaching 2, so x is the variable that is changing. Pi is constant, so 5 pi would also be constant. So as x approaches 2, 5 pi will approach 5 pi. As for the next limit, the limit as x approaches 72 of x. Since x is approaching 72, then x is not a constant. Using our basic property, since x is approaching 72, then x is approaching 72. Next up, the limit as x approaches 4.2 of c plus 1. Because x is approaching 4.2, then x is our variable. Even though c is a variable, in the eyes of this limit, it is considered a constant value because it is not changing, it's only x that is changing. So as x approaches 4.2, c plus 1 will stay c plus 1, so c plus 1 will approach c plus 1. Lastly, the limit as x approaches pi of x. X is the variable that is approaching pi, and as x approaches pi, x will approach pi. Next, we're going to discuss limit laws that allow us to combine functions where the limit exists. We'll let f and g be defined for all x not equal to a over some open interval containing a. And we're going to assume that the limits as x approaches a of f of x equals L and g of x is m. The sum difference law states the limit as x approaches a of f of x plus or minus g of x will equal the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x, which would equal L plus or minus n. In other words, the limit of the sum and difference of two functions is equal to the sum and difference of the limit of those two functions. So if I'm adding two functions together, I can take the limit of each function separately and add or subtract them together. And we see something similar with the product law and the quotient law. The product law states the limit as x approaches a of f of x times g of x equals the limit as x approaches a of f of x times the limit as x approaches a of g of x, which would be L times m, while the quotient law states the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which is equal to L over m. Now, the quotient law does only hold as long as m is not equal to 0 because we cannot divide by 0. So with these four laws, if I add, subtract, multiply, or divide functions, the limit of those functions would be the sum, difference, product, or quotient of the individual limits. The next three laws do only involve a single function, but these are scenarios that come up quite a bit. The first is the constant multiply law. This is where we multiply a function by a fixed value. So the limit as x approaches a of c times f of x equals c times the limit as x approaches a of f of x, which here would equal c times L. So what the constant multiply law allows us to do is it allows us to kick constant multipliers outside of the limit, and then we can just focus on taking the limit of the function itself. Two similar laws are the power law and the root law. The power law states the limit as x approaches a of f of x raised to the n is equal to the limit as x approaches a of f of x, and that value raised to the nth power. Or in this case, our limit would equal L to the n. And something similar for the root law. The limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x, which here would be the nth root of L. However, there are some restrictions to the root law. The root law holds for all L when n is odd. This is because we can take the odd root of any number. However, the root law only holds if L is greater than or equal to 0 when n is an even root, and f of x itself is greater than or equal to 0. If f of x is negative in the interval that contains a, then we cannot apply the root law for even roots. Another thing to note, these laws also apply to one-sided limits. Since we are stating them for two-sided limits, based off the theorem we discussed last section, the one-sided limits also have these same laws. To take a look at how to use these properties and when to use these properties, we're going to evaluate the following limits given that the limit as x approaches c of f of x equals 3, g of x is negative 2, and h of x is 5. The way we pick which property to use is based off of reversing the order of operations. What I mean by that is the last operation we perform when simplifying, if we plug in values, that would be the first property I would apply. So if we look at the limit as x approaches c of f of x plus h of x all over g of x squared, the last operation we would perform is division. So we will use the quotient rule. And after applying quotient rule, we have the limit as x approaches c of f of x plus h of x all over the limit as x approaches c of g of x squared. In the numerator, we can apply the sum difference laws since the last operation we perform is addition. So after applying the sum difference law, we have the limit as x approaches c of f of x plus the limit as x approaches c of h of x. As for the denominator, we can use the power law since we're squaring g of x, and that gives us the limit as x approaches c of g of x quantity squared. Now from there, we can evaluate our limit for each individual function. As x approaches c, f of x approaches 3, h of x approaches 5, and g of x approaches negative 2. If we simplify from there, we get that our limit would be equal to 2. Now we'll find the limit as x approaches c of f of x minus g of x h of x quantity cubed. Again, just like before, the last operation we perform when we simplify will be the first operation we'll apply. The last operation we perform when we simplify is the cubing, which means our limit is equal to the quantity of the limit as x approaches c of f of x minus g of x h of x all to the third power. To break it down farther, the last operation we would now perform is subtraction. So we'll use the sum difference law, which would equal the limit of f of x minus the limit of g of x times h of x. And in our second limit, we can apply the product rule, and now we can evaluate each individual limit using what was given. And when we do the arithmetic, we get that our limit is 2,197. One of the points we emphasized in the last section is when we're discussing the limit as x approaches c, we're discussing the behavior of f of x around x equals c, and not describing what's going on at x equals c. This is different than when we evaluate f of c. F of c represents what our function value is at x equals c and doesn't care about what's going on around x equals c. Certain class of functions have a distinct property that tells us what's going on at a function is consistent with what's going on around the function. In other words, the limit as x approaches c of f of x will equal f of c. When a function has this property, we're going to refer to it as direct substitution. Direct substitution is evaluating a limit by plugging in what x is approaching into the function to evaluate the limit. In other words, the limit as x approaches c of f of x equals f of c. As we go through this unit and this course, we will learn about different classes of functions where we can evaluate the limit through direct substitution. For our first family of such functions, we'll let p of x and q of x be polynomials and let c be a real number. The polynomial law states that the limit as x approaches c of the polynomial p of x equals p of c. The reason why this is true is a combination of the sum and difference laws, the constant multiplier law, mixed with the two basic results we discussed at the beginning. Thanks to those laws combined, we can use direct substitution to evaluate the limit of a polynomial. The second family will be rational functions. The rational limit law states the limit as x approaches c of p of x over q of x equals p of c over q of c. And this holds as long as q of c is not 0. The reason why this is true is rational functions are the quotient of two polynomials. So thanks to the combination of our polynomial law with our quotient law, we can evaluate rational limits using direct substitution as long as our denominator is not 0. Now, thanks to these two laws, we can evaluate the limits in example 3 much quicker. First, we'll find the limit as x approaches 2 of 3x to the fourth minus x squared plus 5. Since 3x to the fourth minus x squared plus 5 is a polynomial, thanks to our polynomial law, we can evaluate with direct substitution. Meaning, to evaluate our limit, we just have to plug 2 into our function. Now, work out the arithmetic, and we get that the limit is 49. For our next example, we have the limit as x approaches 4 of 3x plus 4 over x squared plus 4x plus 2. 3x plus 4 over x squared plus 4x plus 2 is a rational function, so we can go ahead and plug 4 in to evaluate our limit. Now that we have 4 plugged in, we can do the arithmetic, and we get that the limit is 8 over 17. Thanks to the laws for polynomials and rational functions, we're able to evaluate our limit much quicker simply by plugging in what x is approaching. If you recall from the quotient law, the limit of a quotient was equal to the quotient of the limits, so long as the limit of the denominator was non-zero. And we learned in algebra, anytime we entered a value into the function and it caused us to divide by 0, the function was undefined. When it comes to limits, what we usually perceive as something being undefined may actually tell us nothing at all about the limits. This brings us to what we call indeterminate forms. An indeterminate form is a type of expression that arises when evaluating limits where the standard method cannot determine a definitive value. In other words, when we try to use direct substitution to evaluate the limit, an indeterminate form is a result that actually tells us nothing about the limit. The limit may exist, we can't tell for sure. An example of such an indeterminate form is 0 over 0. The reason why 0 over 0 is an indeterminate form is if we take a look at the two examples below, the limit as x approaches 2 of x minus 2 over x squared minus 4 equals 1/4, which we can verify through a table or the graph. Meanwhile, the limit as x approaches 2 of x squared minus 4 over x minus 2 equals 4. Which again, we would see from a table or a graph. However, if we did try to apply direct substitution and plug 2 in, both numerator and denominator in both examples would be 0, meaning we're getting a 0 over 0 limit. So here, despite us getting 0 over 0, we do actually have a limit of these functions. But how can we still try to use the direct substitution method when we obtain a 0 over 0 or in the future other indeterminate forms? The following theorem is going to tell us that we can try to simplify or rewrite our function in such a way where direct substitution may be able to work. In this theorem, we're going to let a be a real number, and we're going to let f of x equal g of x for all x not equal to a in an open interval containing a. If the limit of f of x and g of x as x approaches a exists, then the limit as x approaches c of f of x equals the limit as x approaches c of g of x. So if we take a look at the x minus 2 over x squared minus 4, x squared minus 4 can be factored. Thanks to a difference of squares, x squared minus 4 factors to x plus 2, x minus 2. Now, we're conditioned to think that if we cancel out the x minus 2's our common factor, then the x minus 2 over x squared minus 4 is equal to 1 over x plus 2. That's only partially true. These two functions are only equal as long as x is not equal to 2. This is because I can't plug 2 into the x minus 2 over x squared minus 4, but I can plug it into 1 over x plus 2. But around 2, these two functions are equal. So thanks to this theorem, The limit as x approaches 2 of x minus 2 over x squared minus 4 is equal to the limit as x approaches 2 of 1 over x plus 2, because these two functions are equal for any other x value other than 2. Now with the 1 over x plus 2, if we use direct substitution, we get the 1/4 that we stated above. And the same thing goes for our second example. X squared minus 4 over x minus 2, after factoring and canceling out common factors, would be equal to x plus 2 as long as x is not 2. So the limit as x approaches 2 of x squared minus 4 over x minus 2 equals the limit as x approaches 2 of x plus 2. X plus 2 is a polynomial, so we can direct sub, and we get that the limit is 4, as we stated above. So you can see that the 0 over 0 does not tell us the limit does not exist, nor does it tell us a definitive answer as to what the limit is. So anytime we see 0 over 0, we are going to have to rewrite our function, so that way we can hopefully simplify and be able to come up with a definitive answer. Now we're going to look at a couple of common strategies that will allow us to rewrite functions when we run into the 0 over 0 indeterminate form. One thing to keep in mind, anytime you do try to evaluate the limit of non-piecewise functions, the first thing you should do is always try to use direct substitution. So if we look at the limit as x approaches 1 of x squared plus x minus 2 all over x squared minus 6 plus 5, which is a rational function, so we can try to use direct substitution, we get 1 squared plus 1 minus 2 all over 1 squared minus 6 times 1 plus 5, which is 0 over 0. But remember, 0 over 0 does not mean the limit does not exist. It just means we have to rewrite our function in order to evaluate. Since we have the 0 over 0, we need to try to rewrite this rational function so that way we can try direct substitution again. The common strategy we use for rational functions is we'll factor the numerator and denominator and then try to cancel any common factors. The numerator factors to x plus 2 times x minus 1. The denominator factors to x minus 5 times x minus 1. X minus 1 is a common factor, so we can cancel out the x minus 1s. So our limit equals to the limit as x approaches 1 of x plus 2 over x minus 5. Since we did quite a bit to try to rewrite this function, let's go ahead and now use direct substitution, and we get that the limit is equal to negative 3/4. Next, we'll find the limit as x approaches negative 5 of x cubed plus 125 over x plus 5. Just like in the previous example, if we plug in negative 5, we will get 0 over 0, which is an indeterminate form, which tells us we do need to rewrite our function in order for us to evaluate. The hard part of this problem may be the factoring. There are two ways we can go about factoring. 125 is a perfect cube, more specifically 5 cubed. One of the special factoring rules we've learned before is the difference and sum of cubes. That is, a plus or minus b cubed factors to a plus or minus b times a squared minus or plus ab plus b squared. So if we apply this formula, our numerator factors to x plus 5 times x squared minus 5x plus 25. A second way we can go about factoring, if you recall from pre-calculus, we learned the zero factor principle. The zero factor principle tells us if we know c is a factor of a polynomial, then x minus c is a factor of that polynomial. Well, since negative 5 made our numerator 0, that means x plus 5 is a factor of x cubed plus 125. From there, we can perform long division. If you need a refresher on how to perform long division of polynomials, please see my pre-calculus playlist in this channel. One of the videos goes over how to perform division of polynomials. And we do get through the division that the other factor of x cubed plus 125 is x squared minus 5x plus 25. So there are two ways we can go about factoring, one using special formula, the other way using division that we learned in pre-calculus. Now, as for the denominator cannot be factored any farther. Now we can see that the x plus 5 is a common factor that we can cancel. And now we're taking the limit as x approaches negative 5 of x squared minus 5x plus 25. And if we use direct substitution, we get that our limit is 75. Next, we'll find the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Unlike the previous examples, this function is not rational nor is a polynomial. However, thanks to our basic properties we've already learned, it turns out the limit of this function can be evaluated using direct substitution. If we apply the properties, we will wind up with the square root of 9 minus 3 over 9 minus 9, which is precisely what we'd get through direct substitution. But unfortunately, this would give us 0 over 0, which again is indeterminate. Since this is not a rational function, we need a new strategy to help us evaluate this limit. The strategy we're going to use when we have square roots, we're going to rationalize the numerator or denominator. So erasing our old work, here since our radical is in the numerator, we want to rationalize our numerator. Now usually in college algebra or pre-calculus, we're used to rationalizing denominators, but for the sake of rewriting here, we do want to try to rationalize the numerator. The way we rationalize the numerator is we want to multiply the numerator by its conjugate, which is where we switch the sign in the middle. So the conjugate of the square root of x minus 3 is the square root of x plus 3. But whatever I multiply to the numerator, I must also multiply to the denominator. From there, I can FOIL out the numerator. And when I FOIL using a difference of two squares, I get that the numerator becomes x minus 9. As for the denominator, ideally, I do want to get rid of that x minus 9 since it was causing my denominator to be 0. So even though it's tempted to FOIL out the denominator, we're going to leave it factored so we can try to cancel out the common factors. So we'll leave the denominator as x minus 9 times the square root of x plus 3. X minus 9 is canceled, and we get 1 over the square root of x plus 3. Plug in the 9. We get 1 over the square root of 9 plus 3, which is 1/6. So anytime you have the 0 over 0 indeterminate form with radicals, try rationalizing the numerator or denominator depending on where that radical is located. Now we're going to evaluate the limit of 1 over x minus 1 over 4 all over x minus 4. This function is technically a rational function. Even though it's not a polynomial divided by a polynomial, if I divide a rational function by a rational function, it is still a rational function. And keep in mind, polynomials are rational functions. So if we do the rect sub, we do get 0 over 0, which means we do need to rewrite our function to help us evaluate the limit. Now, our function right now is not written as a polynomial over polynomial, so we can't really factor it to cancel out any common factors. It doesn't have any radicals, so we can't rationalize anything, but it is a complex fraction. The common strategy used to rewrite complex fractions is to clear those complex fractions. So to clear the complex fractions, we can multiply the numerator and denominator by the least common denominator of all of the smaller fractions in the bigger complex fraction, which here would be 4x. So we'll multiply top and bottom by 4x. In the numerator, we'll distribute. As for the denominator, since the x minus 4 is causing us to have 0 in the denominator, I am hoping to cancel it out. So we'll keep our denominator factored for now. Now we can simplify the two fractions in the numerator, and our numerator becomes x minus 4. And we can see now x minus 4 is a common factor in the numerator and denominator. So we'll go ahead and cancel. We get the limit as x approaches 4 of 1 over 4x. We can plug in the 4, and we get that our limit of our function is 1 over 16. The limit of most elementary functions can be evaluated through direct substitution. However, piecewise functions cannot be evaluated through direct substitution. The reason being is when x is approaching a value where our piecewise function transitions from one equation to the other, the behavior is no longer consistent enough for us to use direct substitution. So if we take a look at the limit as x approaches 0 of f of x, I can't use direct substitution to help me evaluate. What we'll do instead is we'll evaluate our one-sided limits. If our one-sided limits are equal, then the two-sided limit exists and is also equal to that same value. The way we're going to evaluate our one-sided limits with our piecewise function is we have to consider what f of x will be as x approaches that value from the right or the left. First, we'll take a look at how our function behaves as x approaches 0 from the right. If x is approaching 0 from the right, that means we're starting from a point to the right of 0 and tracing our graph closer and closer to 0. Well, if we're to the right of 0, that means we are bigger than 0 as we approach. So we want to use the condition that represents x values that are bigger than 0, but are also close to 0. Well, we can see that the middle condition is that 0 is less than x, which is less than 2. Well, this accounts for values that are just slightly bigger than 0. So as x approaches 0 from the right, our function is equal to x squared plus 2, since that is the equation related to the condition 0 is less than x, which is less than 2. X squared plus 2 is a polynomial. Even though we're taking a one-sided limit, the laws we presented were for two-sided limits. So if a law holds for two-sided limits, it will also hold for the one-sided limit. So we can evaluate our limit by plugging in 0, and when we do, we get that the right-hand limit is 2. As for the left-hand limit, x is approaching 0 from the left. So we want to look at the condition where x is less than 0. So if we're approaching 0 from the left, that means we're starting with a point smaller than 0 and getting closer and closer to 0. So we want to look for the condition where x is less than 0 but close to 0. And we can see that would be the first condition. So as x approaches 0 from the left, our f of x equals 2, since 2 is the equation associated with the condition of x being less than or equal to 0. As we discussed before, all of our laws were presented with two-sided limits, so they also hold for the one-sided limits. So our limit as x approaches 0 from the left will be 2. Since our two one-sided limits are equal, then our two-sided limit as x approaches 0 of f of x will also be 2. Next, we're going to find the limit as x approaches 2 of f of x. Just like before, we'll break it down to left and right-hand limits. So we'll start by evaluating the limit as x approaches 2 from the right, which means we want to look for the condition where x is slightly bigger than 2, which will be our third condition. So as x approaches 2 from the right, f of x will be equal to 4x minus 1, since 4x minus 1 is the equation associated with the condition of x being greater than or equal to 2. 4x minus 1 is a polynomial, so we can use direct substitution, and through direct substitution, we get that the limit is 7. Next, we'll find the limit as x approaches 2 from the left. When x approaches 2 from the left, we are slightly smaller than 2, which means we are looking at the middle condition. So as x approaches 2 from the left, f of x behaves like x squared plus 2, which is the equation associated with that condition of 0 is less than x less than 2. And if we use direct substitution, we get 6 as our left-hand limit. So here, our left and right-hand limits are not equal, which means our two-handed limit does not exist. So be very careful with piecewise functions. Anytime you work with a piecewise function, you're trying to evaluate the limit, break the limit up into right and left-hand limits, and evaluate each one individually.